Hi and welcome. This is nuLUCA Pavilion's Intro to Grasshopper tutorial. This is part 1. Venus's flower basket. That's the name of a marine organism, but we'll get to that in a little bit. First, just a quick overview in case you're very new to Grasshopper. This is Rhino, and this is Grasshopper. This is a Grasshopper canvas. Grasshopper is a plugin for Rhino. It runs inside Rhino. So this tutorial is an intro to Grasshopper, but it's also an intro to computational design. It's a glimpse into computational design more broadly and a glimpse into biomimicry. And we bring in biomimicry because computational design and biomimicry go really well together. Computational design is a wonderful way to explore biomimicry, and vice versa. Biomimicry is an excellent way to explore computational design. And so that's what we'll be doing today, an introduction to Grasshopper that examines the patterns in this class sponge. This is Venus's flower basket. This is what we'll be modeling today. And relative to some other intro to Grasshopper tutorials I've seen, this will be pretty involved, but I'm going to go very slowly and explain everything in detail. And I'll assume you have no experience with Grasshopper or with scripting or with this kind of digital modeling. It's very different than drawing on the screen, drawing curves, or modeling forms directly like in AutoCAD or SketchUp or basic Rhino. And so it really is just a different language, but a language that allows you to do so much more with digital modeling than you probably ever thought possible. Once you learn Grasshopper, you'll be doing things that you never imagined you could do. And you'll be thinking about space and design and so many related concepts in completely new ways. And so in this tutorial, we're going to go through an example problem, something we'd like to model. And like almost all tutorials on nuLUCA Pavilion, we're following a model from a natural system, from a living system. And there are lots of reasons for this. One is that living systems are incredibly, incredibly complex. And also they're very beautiful in their complexity in the kinds of connections that they have. And one skill that's very important to build when you're learning Grasshopper or learning computational design is learning how to abstract down, pull out the important pieces from a very complex problem or a very complicated system. And there is quite literally an endless supply of beautiful examples in nature, of beautiful problems to try to solve that can help us get a deeper understanding of complex problems and can help us develop different perspectives and different ways to approach problems in design. And even beyond the fact that this is a really good way to learn a new language or learn computational design, models in nature, systems in nature, patterns in nature are in and of themselves solutions to complex problems. The patterns that we see all around us in natural systems and the patterns that we look through on nuLUCA Pavilion have all evolved as optimized solutions for different sets of problems. They're all very sophisticated adaptations, and we can learn a lot from them, especially when we examine a little deeper where and how they came about, why they are the way they are. And so examining systems in nature can be for us a guide to understanding complex systems everywhere, to understanding all kinds of human systems, to writing algorithms, heuristics, to sustainable design, to more integrated design, to multifunctional design. There's a lot to gain from these different perspectives. But for this first one, we'll take a really simple example, something that's very easy to implement. We'll look at a spatial pattern in nature and bring that into Rhino using the language of Grasshopper. And so the broader goals of this tutorial focus on how do we identify a pattern like this? How do we pull out the important pieces of this pattern? And then, of course, how do we write this in the language of Grasshopper? And this will be confusing at first. It is just learning a new language. If you stick with it, though, your growth will be exponential. It'll seem slow at first, but then you'll just start building and building on everything that you know, and it'll start to come very quickly. If you're just starting in Grasshopper, the best way is probably just to follow along for now. Once you get more comfortable, though, you can try to do it your own way. And so I'll walk through very slowly one way to let this pattern exist on different kinds of surfaces. One way to write that into Grasshopper. And one beautiful thing about Grasshopper is there's never just one way to do anything. There are so many different ways you could do this. And so if you're a little more familiar with Grasshopper, I think the best way to learn and to build your skills is to try to do it yourself. And then maybe compare it to the way that I did it. Maybe you did it better. Maybe there are some things to learn from the way that I did it. But if you're very new to Grasshopper, then the best way is probably just going to be to follow along at first until you start to understand how things are fitting together. And then you'll eventually have the confidence to try these different problems on your own. And so before we get into the specifics of Venus's flower basket, and so that we can address another of the broad goals for this tutorial, let's just take a step back and think about what is computational design and what is parametric design. How are they different? What do these terms mean? You might notice throughout these tutorials that sometimes I use the word parametric or parameter in different ways. Sometimes I can be a little messy in the way that I use terminology, and so I apologize for that. But you can think about a parameter as just a piece of data, usually a number. And so what's interesting about parameters in parametric design is that in parametric design, we write the description of a model that takes in parameters as input. And so just like an equation, like a function that we might see in math, for example, f of xy equals x squared plus y, this equation takes in two variables, and the structure, x squared plus y, stays the same. That would be like the description that we're writing in Grasshopper. And so our parameters might be 4 and 7, and the output would be 23. And so parameters aren't exactly like variables, they're close. You can think of Grasshopper script like the function x squared plus y, and the parameters are kind of like x and y. The structure stays the same. All the connections we make in Grasshopper are the connections, the structure, the x squared plus y. But the parameters x and y can easily be changed, and the output we get, in this case 23, is our model. And this changes a little as we change x and y. So don't worry too much about this right now. It's just important to understand that with parameters, we essentially have an infinite number of models with one description, because we can change all of the parameters and immediately we have different models that are responding to those changes. So this is a pretty good quote, although a little ornate, but it's saying when we have a parametric model, we're at once able to, like it says here, able to relate to a plurality of different alternatives. And there's a few interesting things to think about in this quote. This part's pointing out that in parametric and computational design, we're not designing defined objects. Instead, we're designing processes. We're designing processes of design. And this relates to form as a record of behavior. The design we end up with is a history of behavior in relation to certain requirements. When we're designing forms at this level, the form contains information about the history of its own behavior and information about the history of its environment. Similar to an organism or a living system that contains information about the history of its environment and information about the history of its adaptation to it. And when you're describing something at that kind of depth, you're not really describing what that design would be once, you're describing what it could be in an infinite number of different scenarios, in all kinds of different environments. And then from there, we can start to bring in information we've learned about a specific organism or a specific living system and how that organism or system adapts to different environments. And we can also bring in information specific to the environment we would like our design to adapt to. We can describe our specific environment or pieces of it in our digital model, and then we can let our design adapt to that environment. And so the boundary between the object and the environment begins to blur. It disappears. The object is its environment. It's shaped by its environment, and it helps shape its environment. And so you might notice sometimes I'm saying parametric design and sometimes I'm saying computational design. Computational design is kind of a level deeper than parametric design. Parametric design fits within computational design. It's kind of like a simplified version or a simplified area. Just so you know what I'm talking about when I use these terms, parametric design, adjusting parameters, like Grasshopper, like Dynamo. Computational design, working with computations outside of our own minds. So this includes parametric design, algorithmic, generative, even material computations, so analog computations that occur in the real world or any living organism in a non-living material as a material computes its own form, finds its own steady state or its own resonance. In Grasshopper, on the surface is mostly parametric, but you can definitely do some more sophisticated computational things in Grasshopper. It's very easy to do that. In Grasshopper, you can describe an object or an entity as part of an environment. You can describe the goals, physical interactions, relationships all at once. So an object adapts to its environment. It changes shape according to changes in the environment. Even if your final design is static, even if it's a stationary object, the design process can include time. That form can be a growth or an adaptation that's specific to where your design will live. So we can design, we can experiment, we can visualize, and we can see relationships and interactions from different perspectives. And so that brings us back to why are we exploring this through the lens of nature, through the lens of living systems? And it's that key point. It's because in parametric design and in computational design more broadly, we have the ability to describe a system through which a design emerges, just like in nature. So living systems are not static objects, and they never exist outside the context of their environment. They are entirely part of their environment. They are formed by their environment. They are a response to their environment, and they shape their environment. A vine's never a vine on its own. It would never be the vine it is without the patches of light coming through the canopy, the patterns created by other leaves without the organisms that wrap around it, and the microorganisms that cover it without the moisture in the air, without the carbon dioxide, without other gases, without gravity, without day and night, without seasonal changes. The form and everything about it is an expression of the environment. And so computational design gives us the opportunity to think about design in a similar way, to think about all the constraints that are part of that environment, to think about all the opportunities that exist within that environment, and to think about the goals that we would like for the function of our design. What would we like our design to do? And we can build all of this into the descriptions of our designs, and we can test and fine-tune from there and let a design emerge from that process. And so again, we're not usually designing forms. Instead, we're describing and curating the logic and relationships from which a solution is born. And that's what nature does. And that's why biomimicry is such a wonderful way to teach these methods, these computational methods. And so a lot of times when we're trying to do biomimetic translations or trying to do biomimicry, trying to use something in nature as a model for our own design, we can oftentimes run into problems of scale or material or environments that are so different that it's very hard to decide what part of a design in nature would work in a human design. It's very hard to make that translation. And so that's always something you need to pay attention to, and professionals in this field get very good at learning where and how to abstract out design principles. But when we're working in computational design, it's not necessarily easier, but there is this very interesting advantage, this opportunity to kind of align a way of thinking and describe a way of thinking about a problem, an opportunity to kind of align with the logic of nature in a different way. And if we look at this quote, this is kind of pointing to why this can be the case in a lot of different scenarios. When we're thinking about algorithms, it's the logic we're interested in, and that is so oftentimes independent of the specifics of a problem. Instead, we can focus on categories of problems or the specifics of a language. In our case, going from the language of a natural system to something very defined like Grasshopper or C# or Python. Nature is fantastically clever with its logic in the way that it solves problems, and that kind of problem solving translates beautifully to computational design. But back to the glass sponge, back to Venus's flower basket, computational design is also great if we're doing something like that, doing something closer to modeling form. If we are just translating a spatial pattern, because remember, in nature and in computational design, we need to consider both spatial and temporal patterns, patterns in space and patterns in time. If we're looking just at space, at a pattern in space, like with the glass sponge, like this checkerboard, these squares, this 0-1 pattern, we can translate those patterns into Grasshopper very easily, and then that pattern can live on different surfaces. Spatial patterns that we describe in Grasshopper can live in different environments and adjust to those environments very easily. In our case, this is just going to be putting this pattern onto different surfaces. And so now we can get back to our simple example. We are looking at Venus's flower basket and pulling out the important parts of this pattern, the parts of this pattern that allow it to perform a specific function. And function is the very important thing to keep in mind here. A great resource for functions is Biomimicry 3.8's Taxonomy of Functions. It's a translation tool for designers to help them move from what they'd like their design to do to a language that's a little closer to biological texts, words, phrases, or ideas to help them comb through research describing biological systems. If you want to explore this taxonomy, if you want to explore nature from a designer's perspective or understand better all the hidden functions and the beauty of nature all around us, you can visit asknature.org. There's a lot there. So when we're using biomimicry to design, when we're pulling out patterns in nature, those patterns need to perform a function. Because biomimicry is a performative design methodology, patterns in nature are associated with different functions. They have purposes, they help organisms or systems. They are in some way an expression of that evolution. So when we pull out a pattern from nature, the reason we're doing that is so some of that function comes with, and it's now inherent to our own design. And in the case of the glass sponge, the function is to provide structural integrity with minimal material. And so we have a strong structure that is also lightweight, and that comes from the pattern that we're pulling out. And we'll be following this paper in the journal Nature. This paper was put together by researchers at Harvard, and thanks to them, we don't have to do any of our own original research, and we don't even have to look very far. We don't even have to look very far to see what parts of this pattern are contributing to the structural integrity. There are some good hypotheses in this paper that we can follow. This paper describes the important elements of this pattern, and it is a very high-level abstraction because you'll notice, looking at this photo here, there's a lot more to this structure than this simple abstracted pattern. There's a lot more than just these squares and these cross braces. There's this larger spiral going around, and there's just a lot of very complicated things going on here. And so, like everything in nature, nothing has just one function, and that's true for the structure of this glass sponge. It's not just there to provide structural support. So this paper here that's examining the fluid flow through the sponge looks into some overlapping functions of the sponge's silica structure. This paper is looking at the lattice also, but beyond the mechanical properties, these skeletal motifs, these patterns, also have another function related to optimization of the flow physics. That's what they're pointing out here. And so this is not just to reduce the overall hydrodynamic stress, which is of course related to the function I just mentioned, provide structural integrity, but also to support coherent internal recirculation patterns. This is all coming from the more complicated structure that we see, and the specific functions here, the purposes of this, have to do with filter feeding and sexual reproduction. And so this is all beyond the tutorial that we're doing here, but it's important to think about the fact that in nature, systems are way more complex, and they're addressing so many issues and so many problems. And in nature, organisms aren't just doing things for themselves, they're supporting each other. The functions they perform are woven together to support entire ecosystems. All the complex fluid dynamics that we see coming from this glass sponge, this isn't just for the benefit of the glass sponge itself. These forms have evolved to support a glass sponge shrimp, a certain family of shrimp that have a symbiotic relationship with this glass sponge. So the eddies and fluid movements caused by this complicated form are capturing things like plankton and marine snow from the ocean around and gathering nutrients not just for the glass sponge, but also for these little shrimps. And these shrimp pair up and they kind of choose a house. A glass sponge is a house. These are mating pairs that settle down in these glass sponges, and the sponges help them collect nutrients and provide shelter while the shrimps clean the structure and they grow old together. And they grow so big that they can't ever leave. They have offspring, and the offspring are small enough to leave, and they go off and find their own glass sponges, but these two shrimps get trapped in there forever, and so it's also a love story. And it's the reason Venus's flower basket is sometimes given as a wedding gift in Japan. And so this is all beyond our tutorial here. It's amazing to think about how beautifully all of these functions were combined into this one elegant structure. But for our tutorial, we're just looking at the mechanical properties of this simple pattern. And so if we go back to this paper, that's exactly what they were looking at, the mechanical properties. They did a number of tests, measuring things like buckling strength, and comparing them to other patterns like traditional trusses and slight variations on this specific pattern, like these. And so when we're talking about strength with minimal material, this was a surprisingly strong and efficient design. And so if we zoom back in on just one of these squares again, there are some specific ratios we can notice. If we set this length to L, then where these crossbeams meet is at L divided by root 2 plus 2. And if we zoom in on this area down here, if we consider the diameter of these tubes, there's also a pattern here. The diameter of the larger one, of the tube that makes up the squares, is about 0.1 times L, 0.1 times the length of one square segment. And the diameter of the smaller one is about half that, about 0.05 times L. And so remember, of course, these are abstractions. These are very general. These are generalizations. Of course, in the actual glass sponge, these aren't going to be perfect squares. As a matter of fact, when this pattern, the 0-1 cross-beam square pattern, actually dominates the structure, the glass sponge itself is very flexible. It's still forming and flexing and changing to fit into the specific environment that it's in. And then as it matures, more material fills in and these spirals go around the perimeter and it becomes rigid. But there's so much unpredictability that living organisms need to be equipped to handle. The world is very noisy. It's not possible to predict exactly what an organism will need. And so there's variability in these patterns, and that makes them much better. That makes them much more finely tuned to their specific environment. This reflects the randomness that nature has to respond to, and it's better if the design can vary a little from point to point, from moment to moment. But for us, of course, it's easier to abstract out a reproducible pattern, in this case, a spatial pattern. In later tutorials, we will go into abstracting patterns at deeper levels, at the level of an algorithm, a pattern in logic, and this can lead us to variability from point to point or from moment to moment in our own customized solutions. Okay, enough wandering. Next, we'll jump right into Grasshopper.